Welcome back to Discovering Geometry with Mrs. Berry. This is lesson 34. In this lesson, we'll have an algebra review and do special properties of special parallelograms. So our algebra review will be solving systems of linear equations. We'll look at using both substitution and elimination. Then with special parallelograms, we'll have a double-edged straight edge, rhombus properties, and rectangle properties. In a system of equations, we have two or more equations with the same variables. If they're linear equations, we'll have an x and y as their variables. A solution to the set would satisfy all equations in the system. So if that solution is to a linear equation, it would be a point on that line. If the point is a solution, you could substitute in the xy coordinates for the x and the y in the equation, and the equation would be true. If it's two or more equations, it would be true in each equation that you have. Graphically, the solution to a system of linear equations will be where the lines intersect. You can estimate the solution by graphing, but the solution doesn't always appear on a grid intersection. So finding an exact solution often requires algebra. That's what we'll be looking at today. Here we have a line in blue and a line in red. The point of their intersection lies at 1, -1. That is the solution to these systems of equations. Now using them with substitution, there are two common methods to solve a system of equations with algebra: substitution and elimination. Substitution would be solving one equation for one of the variables, either x or y, and then substituting that in for the second equation. If both equations are in slope-intercept form, this is really quite simple. Here's an example. Y equals 2x plus 4 and y equals 1/2 x minus 5. Both of these equations have a y equals something. So it would be very easy for us to put in the 2x plus 4, where the y is in the second equation. Because it's equal to y in this equation, we could substitute it in for the y in this one. So I would say 2x plus 4 is equal to 1/2 x minus 5. Now I'm just grouping my like terms together, so I'm going to move the 1/2 x to this side, and I'm going to move the 4 to the other side. On this side, I have 2x minus 1/2 x. That gives me 3/2 x is equal to, on this side, -5 and -4 is -9. To solve this, I'm going to multiply by the reciprocal so that I'll have 1 in front of the x on this side. So 2/3 times 3/2 gives me 1. So I have 1x is equal to -9 times 2/3. I'm going to reduce and divide 9 by 3 and get 3. So I'll have -3 times 2, which is -6. So my x coordinate is going to be -6. How do I find my y? Well, I just substitute in -6 in either one of these equations. This first one seems a little bit easier, so y is equal to 2 times x, my x is -6, plus 4. -2 times -6 is -12, plus 4, so y is equal to -8. What if I had chosen the other equation to substitute it in? Let's see. Y equals 1/2 times x, which is -6, minus 5. Well, -6 times 1/2 will give me a -3 minus 5. And -3 minus 5 is a -8. So you can see it doesn't matter which equation we choose to substitute back into, we're just solving for our y after we get our x. That makes the point of intersection, or the solution to this system, as -6, -8. So our final answer is just this point. And we got that by solving for x and then substituting in and solving for y. You can also substitute even if the equations can't easily be set equal. So on the last one, they were both y equals something. It was very easy to set them together. But we could solve this system another way. I can solve this one for maybe the x variable. I could solve for the y as well, but it's a little more difficult. I could solve this equation for either the x or the y. I'm going to choose to solve this second one for x. That means I want x all by itself on one side of the equation. To do that, I'm going to move this 2y over. So I'm going to add a 2y to both sides of my equation. This becomes 0 and leaves me with just the x. And this is now x equals 8 plus 2y. Now, if this is what x equals from this equation, now I can take this and put it in for the x in my other equation. Y minus, I'm going to put it in parentheses because of this minus, 8 plus 2y equals 2. Now I need to not forget that this minus goes through everything in the parentheses set. So I'm going to distribute the negative sign and say y minus 8 minus 2y equals 2. I'm going to combine my like terms on this side, so I get negative y. I'm going to add the 8 to both sides so that I get 10. If negative y equals 10, I could multiply both sides by a negative 1 to get that a positive y equals a negative 10. Now, once I have my y, I can go back to either equation to solve for x. I could even go to this middle ground where I solve for x by itself and plug in y to find what x is. I'm going to just choose this first one. So if y is negative 10, and then I have minus x equals 2, I'm going to add the 10 to this side. I'm going to say that negative x is equal to 12. And if negative x is equal to 12, then positive x is equal to negative 12. My solution is then the point negative 12, negative 10. Now, solving by elimination can be more useful if the equations are in standard form. What we will do is add the equations together after ensuring that one of the variables will cancel out or be eliminated when we add them together. So we're going to solve this system. 6x plus 4y equals 2, and 4x plus 2y equals 3. If we were to straight add these equations, we would have 6x plus 4x is 10x, and then 4y and 2y is 6y. I would not have eliminated either variable, and that's what I'm trying to do. So this problem would best be done if we multiply one entire equation by some number so that when we add them together, they would eliminate a variable. Because both of these are positive, we definitely want to use a negative number. But even then, these numbers are not equivalent. What if I take this second equation and I multiply everything by a negative 2? I like to write it like this and make sure that that negative 2 gets distributed to all three parts. So I have negative 8x minus 4y equals negative 6. Now if I take my first equation and add it, 6x plus 4y equals 2. When I add these equations together, you can see that my minus 4y and plus 4y eliminate each other and make it 0. Over here on the x's, I have a negative 2x, and that's equal to a negative 4. Negative 2x plus 0, I can ignore that plus 0, and now I have negative 2x equals negative 4. I'm trying to solve for x, so I'm going to divide by negative 2, and I have that x is equal to a positive 2. That was pretty simple instead of trying to rearrange all of these and get an x or a y by itself for substitution. So you can see how it's useful when it's easy to multiply some number that you could eliminate at a variable. Once I have my x, I can go back to either equation or even this one that I multiplied things by and put in 2 for x to solve for y. I'm just going to choose the second one. It seems convenient, but any of the equations would have worked. Sometimes elimination means a little bit more work in finding the second coordinate. 8 plus 2y equals 3. So now I'll subtract the 8. 2y is equal to -5. I'll divide by 2 and get that y is equal to -5 halves. So my x-coordinate is 2 and my y-coordinate is -5 halves. That would be the solution to this system. Now, on to some geometry. In this lesson, we will discover some properties of rhombuses, rectangles, and squares. Do you see the rhombuses in the legs of these scissor lifts? What we discover about the diagonals of these special parallelograms will help you understand why these lifts work the way they do. Our first investigation will be, what can we draw with a double-edged straight edge? So a double-edged straight edge is just a tool, possibly like a ruler, where both sides are going to be very straight and parallel to each other. So you need a double-edged straight edge and maybe some patty paper. On a piece of patty paper, use a double-edged straight edge to draw 2 pairs of parallel lines that intersect each other. Assuming that the 2 edges of your straight edge are parallel, you've drawn a parallelogram. So you're going to draw one like this and then one of them like this. This shape in between will be your parallelogram. Place the second piece of patty paper over the first and copy one of the sides of the parallelogram. Then compare the length of the side on the second patty paper with the lengths of the other 3 sides of the parallelogram. How do they compare? Repeat this investigation with a different width straight edge, double-edged straight edge, if you need further proof. Here's what that looks like. I'm using my ruler to draw both sides. I'm going to turn it and draw another 2 sides. I have a parallelogram in the middle. And you can see that all the sides are the same length. So if 2 parallel lines are intersected by a second pair of parallel lines that are the same distance apart, that's the same width because you use the same double-edged straight edge, then the parallelogram formed is really a rhombus. All the sides are the same length. So now you know a quick and easy way to make a rhombus. If you want to construct a parallelogram that is not a rhombus, you would simply use 2 different double-edged straight edges where they have different widths, maybe a skinny ruler and a fatter ruler, or maybe even a ruler and a note card. Our second investigation is, do rhombus diagonals have any special properties? So we need our rhombus that we just drew and another piece of patty paper or just regular paper. Draw in the diagonals of the rhombus that you created in investigation 1. Now place the corner of the other paper onto one of the angles formed of the intersection of the 2 diagonals. That paper should be a 90-degree angle. So are those diagonals perpendicular? Were you able to fit the paper in there exactly? Recall that a rhombus is a parallelogram, and the diagonals of a parallelogram bisect each other. So the diagonals and the sides of the rhombus form 2 angles at each vertex. In a minute, we'll also fold our patty paper to compare each pair of angles and see what we observe. Here's the first part of that. I'm going to draw in my diagonals, and then I'm going to compare using that. I also used my protractor to measure them, and they are 90 degrees. So we know that parallelograms diagonals bisect each other, and now a rhombus also forms 90 degrees. So they're perpendicular bisectors on this diagonal of rhombuses. Now we're also going to fold our paper at our angles and see what do those diagonals do for those angles. So the rhombus diagonals conjecture. The diagonals of a rhombus are perpendicular because they form 90-degree angles, and they bisect each other. The rhombus angles conjecture. What did we draw in of the rhombus? The diagonals. And those diagonals bisected those angles. So the diagonals of a rhombus bisect the angles of the rhombus. So far, we've made conjectures about a quadrilateral with 4 congruent sides. So now let's look at quadrilaterals with 4 congruent angles. What special properties do they have? So what's the definition for a rectangle? A rectangle is an equal angular parallelogram. What is the measure of each angle of a rectangle? We know that the quadrilateral sum conjecture says that all 4 angles add up to 360. If it's an equal angular parallelogram, then what's 360 divided by 4 angles? Well, they're all congruent, so each angle must be 90 degrees, or a right angle. For our third investigation, we need graph paper, a compass, and a pencil. Draw a large rectangle using the lines on a piece of graph paper as a guide. Draw in both the diagonals. With your compass, compare the lengths of the 2 diagonals. Draw another rectangle to compare if needed. Recall that a rectangle is also a parallelogram. So all the diagonals of a rectangle are going to have the property of parallelograms. We're going to combine these ideas to complete our conjecture. So here's my graph paper. I'm drawing in a rectangle. I used a ruler to make sure that my lines were straight. Now I'm going to draw in the diagonals. I'm using my compass to compare the lengths, and I find that they're even. They're congruent diagonals. So a rectangle has diagonals that are congruent and bisect each other. Remember, that's from our parallelogram conjecture. Our last thought for today. What if we combine the properties of rectangles and rhombuses? We call the shape a square. We could think of it as a regular quadrilateral. So we can define a square in different ways. We could say that a square is an equal angular rhombus because a rhombus has equal sides. If we also have equal angles, it would be a square. And a square could also be an equilateral rectangle. A rectangle is going to have equal angles. So then if they also had equal lateral or equal sides, it would be a square. So a square is both a parallelogram, a rectangle, and a rhombus. So we can write a special conjecture about a square that combines all of these properties. The diagonals of a square are congruent, just like a rectangle. They are perpendicular, just like a rhombus. And they bisect each other, just like all parallelograms. So those are the properties of special parallelograms.